this presentation, and a trimmed version of it will appear on YouTube. So please beware of that when you are asking questions and so on. We can start. I am Cüneyt Akçora, an associate professor at the College of Business in the Finance Department, and today we have the first one of our two presentations on agentic finance. The first presenter is Alejandro Rodriguez. He's a graduate researcher in the financial technology program at the University of Central Florida. He's finishing his master's in FinTech and also serves as a teaching assistant in corporate finance. His work bridges finance, data science, and AI. And Alejandro's current projects are an agent-based entity resolution pipeline that we are going to present today, and also a decentralized lending protocol on Ethereum. He has a background in Python development and financial modeling. Alejandro is our last semester student, so he is going to graduate in December. He uses large-scale graph analytics and retrieval-augmented LLM workflows. He is passionate about leveraging data-driven insights. He has experience developing predictive models and Neo4j knowledge graphs. Today, we are going to present his work on entity resolution for customer record matching. This is a very dirty data problem, database cleaning. There is lots of money in this business, many startups. Around 10 years ago, we had a research article with a Turing Award winner in this topic, so I am familiar a little bit with the previous versions of this, but now, instead of developing probabilistic models, we are developing large language-based agentic finance models to do this customer record matching. Alejandro, the floor is yours. Please share your presentation and start.
Yep. Can you guys see my screen? Yeah? Cool.
Yes.
Good evening, everyone. My name is Alejandro Rodriguez. I'm with the Department of Finance. As Dr. Akçora said, this is my last semester in my master's in FinTech. So I'll be finishing in December, hopefully. Everything goes right. I'm here to share my research on agentic AI. We developed an entity resolution pipeline that automates it. So yeah, let's begin. So firstly, our agenda. We're going to be talking a little bit about our artificial intelligence, agentic AI, the introduction of LangChain, introduction of LangGraph, highlight the improvements from chain to graph, talk about RAG and its functionality, improvements made on RAG to get to GraphRAG, GraphRAG is used as an architecture, and a breakdown of our existing pipeline for entity resolution. So let's begin. So, origins of AI. Contrary to popular belief, the field of artificial intelligence is not new. The origins of artificial intelligence date all the way back to the 40s. These are top 3 milestones that AI has accomplished. So first, we begin in 1956, where the Dartmouth workshop begins. It formally coined the term of artificial intelligence. In this workshop, participants presented early programs and debated how to mechanize reasoning, learning, language, and creativity. In a sense, uniting the research community to accomplish one goal. Prior to this, people refer to artificial intelligence as machine thinking, automata studies, or cybernetics. Some of the most notable names for this is John McCarthy, which was the organizer of this Dartmouth workshop. Later down the line in 2012, AlexNet wins ImageNet, which sparks a deep learning revolution, proving that neural networks plus massive data and a GPU outperform every existing learning method. Some of the more notable names for this is Geoffrey Hinton, which is known as the grandfather of AI, who recently got awarded with the Nobel Prize for his work. And lastly, 2017, where we get the transformer architecture. This is the backbone of modern large language models. So anything, ChatGPT, Claude, Gemini, anything under the sun, that's basically how they're working. So AI in 2025. AI is a very hot topic. I'm pretty sure you guys have noticed. It's everywhere in the news. Companies have caught onto the potential upside of AI, and they have decided that they need to capitalize. They have realized it's not going anywhere. and if anything, they need to keep investing to enhance its workflows. 2025 marks the switch from AI being used just for chatbots, but rather to do agents that are more capable of executing complex tasks. So, as I mentioned prior to this, we have been using LLMs passively. So what does that mean? We ask it questions and we get answers. Agentic AI is a way of using large language models so they could do more than just give a simple answer. They can figure out a plan, choose actions, and carry out that plan, all while you keep them on the leash. It acts on a goal. This means that you give the agent one broad instruction and it breaks the job into smaller steps by
Sorry,
itself.
Alejandro, we lost your screen. Or is it only me? The
What are
sharing
you guys seeing?
stopped.
The sharing stopped? There? We back?
Yes.
Okay. So here we are. That's what I was saying. It acts on a goal. So you give the agent one broad instruction, and it breaks the job into smaller steps by itself. It grabs the right helper apps. So it could call a web search, database a query, use a calculator, or any giving tool that we're giving the program, right? It learns as it goes. After each step, it checks the results, tweaks the plan, and tries again if needed. It always stays under control. As the engineer or the creator, you can put in checkpoints or safety rules so a human approves anything risky. I want you to think of a GPS. It chooses a route, reroutes when there's traffic, and asks you to confirm toll roads. That's autonomy, tool use, memory, and oversight, what I just described in Agentic AI. So, the Agentic AI toolbox, what do they have to offer? What are the things they could use? Well, we as users get to decide which tools are available for use to our agent. Some of the most common tools are the following. Web search, it enables the agent to look up current facts, so use the web. GraphRAG query, which gives access to a knowledge-based graph to retrieve information. Calculator or code runner, this performs mathematical operations or run code snippets. It has email Slack API, so this sends notifications or asks humans for feedback or permission. And it has a memory store. It's how our agents keep notes of what's being perceived. For this analogy, I want you to think of our agent being a child. I want you to picture that a child's tablet with only approved apps. This kid can pick up the apps that are only in the tablet and will only help them to solve the problem at hand, but it can't install new ones. We as the caregiver decide on what the tablet to keep the pipeline safe and avoiding any memory leakage or sensitive data. So, Agentic AI uses. We were approached by a credit company to help them with fraud detection. Fraud detection for a credit company has many faces, and they all collapse to an entity resolution problem. So, how can companies benefit from this? A common pain point that every company is having is the duplication of customers. Many companies have multiple customers holding space in their databases. This is known as the entity resolution problem. How are they addressing this right now? Well, manually. Someone has to sit down and go through each records, seeing if they're not a duplicate. And if it's a duplicate, then we know there's a fraud. So, what are some other uses? Prior to working in this entity resolution pipeline, I was working on a personal project that had agents pulling information from multiple sources and giving me a recommendation based on the examples I gave it. So I had an idea of what my risk tolerance was and if it was a good deal or not. So, further from that, they could also do customer support. We've seen this already. They're pretty good at chatbots and pulling information from any documents from a company that's providing. So also data aggregation, which is the example I just gave, pulling in financial information from companies and basically putting them all in one spot for me. They could also do report generation, automatic email responses, which the second part of this seminar. The pipeline is about doing automatic email responses. So what is powering our agents? How are we supposed to give it a set of instructions that it needs to follow to complete our task? How are we structuring that? Well, this is where LangChain comes in. LangChain was the first Swiss Army knife. It glued prompts, embeddings, tools, and memory into repeatable chains. LangChain is an open source software framework designed to simplify the development of applications powered by a large language model. At its core, LangChain structures LLM into chains, which are ordered sequences of links, where each link performs a discrete action and passes its output to the next step. It formats an input, it queries the LLM or agent, it retrieves the data. LangChain represented one of the earliest and most widely accepted frameworks enabling LLM-powered agentic behavior. As workflows grew and tasks became more complex, loops, human checkpoints, multiple agents were needed. The linearity that LangChain was offering was not enough. So what happened? LangChain created a new model called LangGraph, which we'll talk about. LangChain marked a critical stepping stone for the path of agentic AI. So this is an example of LangChain. I want you to see the purple boxes that are here. This could be a customer email, a knowledge base, a chunk of text, any documents that are needed for the agent to complete its task. From there, we move to the prompt template. This is basically a fill in the blank sheet with some instructions for our agent. For example, read the email and draft a short reply. Then that gets moved to the model. The prompt gets fed into the model, who's in charge of piecing the information that is received from the template to the formulated response. The raw model output then gets cleaned by the output of the parser, so it's machine friendly. Then we get an action over to the right in the green boxes. That could be, for example, send reply, archive the email, tag urgent. So as you can see, everything is very linear. There's no forks, no loops in the task. This is the major pain point that LangGraph solves, which is the next iteration of LangChain. So, introduction to LangGraph. LangGraph was born out of the LangChain project in late 2023. The LangChain team realized that the real-world LLMs applications need more than just a linear prompt. They needed a stateful cyclical workflow, so not just one-off call. We needed fine-grained control of which agent or what prompt is running. We needed built-in support for human overrides and feedback loops, and a unified programming model to perform multi-agent processes. I want you to look at this picture and think of each node in the LangGraph as a runner on a relay race team, and the state as the baton they carry. So at every handoff, the state accumulates more information, and the order in which this happens is shown by the flow of the LangGraph. So the improvements from LangChain to LangGraph. So LangGraph replaced the DAG. DAG stands for Directed Acrylic Graphs. A DAG is a strict fixed sequence of steps. Once the process begins, you follow that path linearly. Looping is not a thing. So LangGraph replaced this with graph of nodes and edges. This enabled a cyclical workflow where loops are easily implemented. It also offered a centralized state object. In LangChain, we had an output being moved from link to link. LangGraph maintains one single mutable state that gets updated by each node. This provides the user with observability and prompt tweaking. So observability means that we can see how the state is being mutated as it moves along the graph, making it easy for us to detect if anything is not working as intended. We could also analyze how the state is being affected at each decision point. Because observability is now possible, prompt tweaking becomes more efficient and easier to enhance for desired results. It also had explicit edges and entry points. So with LangGraph, we could add normal edges like we did in LangChain from A to B, as well as conditional edges. So a conditional edge would look like if an LLM says continue, we loop back, otherwise we end the task. And lastly, it offers a multi-agent orchestration, which we're going to be using in our entity resolution pipeline, which is basically specialized agents. They collaborate via the share state. So multiple tasks being done to that one state till the task is done. So RAG to GraphRAG. Retrieval-augmented generation is the process that helps LLMs understand the context by integrating internal and external data sources. So how does this happen? We begin with indexing. We embed documents into a vector store. We then go into retrieving mode. So we embed the query and run a similarity search. We then go into augmentation. We attach top case snippets from the similarity search. And lastly, we generate. So LLMs reads the prompt and produces an answer for the user. So where does RAG suffer? When we have a query that requires a multi-hop or path seeking question, for example, which suppliers of Tesla also supply Ford? In normal RAG, text chunks arrive in independent blobs, which gets rid of any structure that once linked them. So essentially, shredding a map into confetti. The question of which suppliers of Tesla also supplies Fords requires our retrieval to keep its structure, because we would be looking for a relationship between two entities, right? With regular RAG, the top chunks will rarely put the relationship within the same chunk, which makes our agent have to bridge the gap by guessing, which often leads to hallucinations, which is false information or a false conclusion, which is something we're trying to avoid. So, GraphRAG. GraphRAG is the newest method of retrieval-augmented generation that stores facts as graphs in a graph as nodes and edges instead of just plain text chunks.
Alejandro,
GraphRAG was the yes.
Can you please
Yes.
move this screen sharing menu at the bottom?
Oh, yeah. There we go.
Okay, thank you.
Yep. GraphRAG was developed in late 2023 as an enhancement to the pre-existing RAG. It leverages a knowledge base to organize information, enabling structured retrieval and multi-hop reasoning for question answering. So how does it work? There's two main components: the usage of LLMs to extract entities and relationships from unstructured data into a graph structure. It also has RAG. This component is enriched by mapping out how said concepts are connected, which helps our LLM handle complex queries and diverse data formats. So, triple extraction. This is the process in which basically our information is being synthesized. The main idea is that we're turning paragraphs into tiny who did what facts so that the graph could understand. In step one, we're breaking these the chunks into short single idea sentences. On step two, we're extracting three parts of our simple sentences, which are subject, relation, and object. This process becomes very useful once the triples are in a graph. Information retrieval becomes more of a pathfinding task rather than a paragraph hunting, which in turn leads us to have a more lightweight and more reliable knowledge base, which in turn reduces hallucinations. So this is how a GraphRAG would look in our database. It's very simplified chunks would look basically into very simple sentences or simple connections. So the main benefits are, once again, disparate chunks. So they're not arriving at the same time, are not directly connected. The triples are a form of capturing the essence of the text chunks in very simple sentences. And lastly, we could put triples into a graph database where we could query it using a query language, similarly to how SQL works, where it has its own language, and you could pull and showcase data in a very organized and clean way. So this is the totality of what our agent would be retrieving. So as you can see, we're still using the vector store or the vector retrieval and using a top K search, exactly like vanilla RAG. But now we're also attaching a piece of our subgraph to enrich the context window for our agent. As you can see, the graph is also able to keep relationships between facts, even though they're not set in the same chunk. If we just depend on RAG, our agent could hallucinate and make up facts, since the top K would be arriving in blobs and we don't have the specific timing, which we kind of need for multi-hop reasoning questions. So GraphRAG's architecture. What do we need for GraphRAG to work? Firstly, we need a knowledge graph. This is where we're going to be storing our data. Usually this is a Neo4j. Neo4j is a native graph database and a graph data platform around it. They were the company that first came in and decided that this is great. They also created something called a cipher, which is basically the way you communicate to the graph what you want to see or how you want your data to be organized. It also requires a retrieval tool, as I said, the cipher. And this is how the GraphRAG retrieves information from the graph. And we tend to give the parameters that we want to retrieve. It also needs a formatter. This is basically needed to transform our node information into relationships, into something that our LLM can read, pretty much. So going from node information to JSON or text, which is what an LLM could read. Lastly, we have our LLM or agent, which this is the brains of our operation or our system. This is the piece that will synthesize the information, formatted retrievals, and answer the queries for us. So this is the workflow of the pipeline that has been created. We will go into detail in every single step, and but this is just how the information will move across the workflow. So first we begin with loading the data in a light pre-process step. We create and connect to our database. We ingest all our data and for our graph database to be created. We then do a creation of helper rows, which is basically indicators of how we want our data to be organized, where we then set up retrieval capabilities. And then from there, we split into both our agents, agent A, who's a categorical agent that will give us a yes, no, or unsure, alongside a reason of why for each decision, pretty much. And then we have our agent B, who is our probabilistic agent that would assign a probability of 0 to 1, them being a match. Our last agent is our manager, which basically synthesizes both the output of both our agents and gives us the decision of a match, unsure, or no match. We then move into decision counting and storing. And from there, we ask the user to help classify and unsure cases. So this is when our agents are unsure how to classify the records, it would put them into a bucket of unsure cases. Those unsure cases would then get prompted to a human. So this is where the human in the loop comes in to help our agents learn and pick up more signals to better classify for the next iterations of data that come into the workflow. And then we export the decisions and records to a database, or it could be in Excel, SQL, anything. So let's begin. So what data set and metrics are we using? The data set that we're testing on is the ABT by, which is a very common benchmark for entity resolution problem. The values in this data set are rather textual and describe various product features. The efficiency of our pipeline will be measured by the following metrics. So precision, it answers the question of my match predictions, how many were right? And recall, it answers the question of all the real matches, how many was I able to find? So the first step, we're loading and pre-processing. In this step, we're cleaning the name of all our products as well as extracting their brand name. I want you to look at the after cleaning sample where the title is cleaned. There's no capital letters and we get rid of any special characters. We're also doing this with brand names. Essentially, in this step is where we normalize our data to be uniform, which will help our building our knowledge base. So the connection and creation of our database and ingestion. So the first code snippet that we see is basically creating a container and creating a connection to Neo4j so they could hold our information and start creating the graphs. After that, in the second code snippet, is a uniqueness constraint. This ensures that when we try to ingest the same data with the same properties, there won't be a creation of a new node. Instead, a merge would happen with the pre-existing node. So this also helps with duplication. After that, we have a Cypher template. And the Cypher template is Neo4j's language of how we want our data to be organized. In this case, we want the products to have the following the properties mentioned. So we want to know where is it coming from, if it's the ABT CSV or the by CSV. We want to know the name of the product. We want the clean title because that's how we will be creating the tokens. We have a normalized brand. So as I said, no capitals, everything is undercased so our agents could understand better. And we have a price point. So basically how much it costs. And lastly, the last code snippet we see is the bulk ingestion of our data. I'm working through a laptop, so like ideally you don't need this. So yeah, this is basically just me putting the information in chunks instead of just letting it all go. Something I forgot about the Cypher template, this is like the English language. So nouns are the nodes, so that would be the entities or the products, while the verbs are like the relationships. So for example, later on, you'll see how it's connected to something else. And there's the connection that says has token. So yeah, we'll see how that builds up. From there, we create helper rows and tokenization. It's in this step where we take each product's clean title and split it into meaningful tokens. So for example, what we see here in the presentation, we have Netgear, Switch, and Smart, just to name a few. In Neo4j, then we create two kinds of helper nodes, brand and name token, and link each product to its brand, which is not in the picture, but later on you'll see it. And has token, which is noticeable in the picture. This means that any two products sharing a brand name or the name token are now connected through the graph, which we'll later use to generate candidate pairs for matching. So now we're setting up the graph retrieval function. In this step, we're grabbing two product nodes and its connections, so brand and tokens, using brand and tokens. Based on that, we pull some of their neighbors with a ranking criteria, pulling those who have similar price for specific brands and tokenized titles. We fetch this subgraph and make it into a JSON, which will then get fed to our agents. The first code snippet that we see here is basically specifying how many neighbors we want for each category. So for example, we want 15 neighbors from the brand, so 15 products that have the same brand. We want 8 of the neighbors that share the same token and a hard cap of 120. So ideally, those two numbers, basically the brand and the token, are arbitrary. They could be anything, but we want to have a hard cap, because if not, our agents would just be pulling the whole graph, which is something that we want to avoid. It basically defeats the purpose of having a graph, because it's lightweight. It's supposed to be fast. It's supposed to be efficient. If you're pulling the whole graph, then it's basically like loading the whole CSV. And this second part that we see here is basically what our agent will receive. So our node information has been formatted into JSON, which is readable by our agent. So our agents and our managers. So let's see. This is the brains of our pipeline, as it's in this step where we give examples to our agents of how to correctly classify and consider if the two products that it's seeing are indeed matches or not. We first begin with agent A, which is a categorical classifier that gives us the following outputs: yes, unsure, and no, as you can see here, alongside with the reason why it's classifying it this way. We then have agent B, who is our probabilistic agent, that similarly to agent A, it looks at the titles and brands of both products, but also looks at the prices and their disparity. It assigns the probability from 0 to 1. From there, we have our manager, who's initiated with the following probabilities. So a high probability of them being a match, which is 60%, and a low probability of 40. So that if agent B is providing us with those numbers or within that threshold, it's going to be a strong signal. That's what it would be considered a strong signal. These will change as the human in the loop comes in. You'll see that later. This is an example of what basically the record will show. It would show both of the products, of course, their IDs, agent A's decision, so they're not a match. Why? Well, the brands differ. Agent B gives us a probability of them actually being a match or being the same product. And then our manager, which basically synthesizes both decisions and says, indeed, they're not a match. From there, we go into the batch evaluation and precision and recall. So we're done building the pipeline. Now we have to test it. These are the results that we got from passing our data for the first time through our pipeline. So our decision counts. We have a match of 1051, a no match of 516, and a need more data of 24. We have a precision of 97% and a recall of 93%. Remember what precision is telling us of my match predictions, how many were right. And recall tells us of my real matches, how many did I find. These are just some to showcase some of the records of this decision. As you can see, the examples are pretty noticeable that they are indeed a match. There's little to no difference within their title. And these are the top, like the least probability of them being the same product. Okay, yeah, from here. So now how does it look in a graph? This is an example of how it would look. We would have within the node that connects them, we would have our agent's A decision. So what our agent A says, yeah, they are a match. The decision of our manager, indeed a match. We have the IDs of our products. So this could be anything. This could be a person. We have a probability of our agent B, and then a reason alongside. So identical brand and very similar titles. This would be an example of what a match will look like. So human feedback. This is where we come in. The unsure cases would be classified by our agents, would get fed to humans so they could classify it manually, saying if it's a match and giving alongside a reason of why it is a match. I just want you to, I'm going to go over both the results before the human and after the human. The matches changed from 1051 to 1068, so that's good. We found more matches. A no match from 516 to 493, and our need more data bucket went up from 24 to 30. Our precision remained the same, so 97% for both, but our recall went up, which is something that we want. We're finding more of the true matches. I want you to look at the need more data buckets. They went up, so that means our manager is not memorizing information, is actually learning from the feedback we're giving it. It's instead of just, if it's unsure, it's not going to guess if it's a yes or a no, or sorry, if it's a match or not. Instead, if it doesn't receive a strong signal from agent A or agent B, then it will just put it in unsure. So it would basically be more precise for us, which is something that we want. Within the graph database, we also could see both the product names. We could see the label, which is the human label of matching. There's a reason that's basically same product and brand. And we also have a user, which adds for accountability for this type of jobs, which is very necessary, which is very good. And yeah. So this is the last step. We're exporting our decisions so they could be easily visualized. We have our product A names. We have our product B names. So basically the pairs that it created. We have the agent A's label. So yes, no, or unsure. We have our probabilistic agent giving us a one from 0 to 1, a range from 0 to 1 being of the two products being a match or not. And our final decision by our manager, they're a match or not. And alongside a reason. So yeah. These were some of the sources that I used for this research. Thank you for attending. I appreciate it. I want to leave you with this thought. If you can turn your problems into paths, then you can turn your paths into agents. Thank you.
Thank you very much, Alejandro. I think the most impressive thing in these agentic AI solutions is that it's kind of out of the box and you get a precision of 0.9 and recall of 0.9. So usually one of these things is not that good.
Yes.
Either the precision is very good or the recall is very good. But in this case, both of them are very, very good. So it is very impressive. Thank you very much. We can take a few questions. We can also take them from Pradeep's class. One question from me is that
we have a question from one of my students.
It's
okay,
actually,
go ahead, please.
Hi, I'm Daria. So I actually have an interesting question. How did you came up with the branding? What was your thought process behind that?
Can you explain what do you mean by the branding?
Like the logo and like how did you came up with the design and the name?
Or for the company?
For
your company.
For the company.
Oh, no. This is the data set. It already has all this information. So like you would have the product names and this is basically code like going through the product name and extracting the brand or the tokens and which you saw from the graph. So it's just basically a parser going through it.
Okay.
So, yeah.
Okay. All right. Thank you.
Yeah, you're welcome.
Yes, Alejandro, my question is that in the final document, you show that you are also writing down the no matches.
Yes.
Why? Because there will be too many no matches, right?
Yeah. Well, ideally, I just wanted to export everything. And then from there, you could, filter anything that you need to see. Maybe there's a mistake, which you could go back and see, which also helps us. For example, right now, the feedback I have, the human feedback is only giving 5 of the human labeled to the agents after. If we have a bigger context window, for example, if we're using Gemini, which has 1 million tokens, then we could pretty much just give everything to it. So yeah, it's to kind of hold some sort of, I guess, check to it. So yeah, any other questions?
I have a quick question. Now, the LangChain and LangGraph, they themselves are not AI models, but they are sort of, you set up a sequence of instructions that are then executed by drawing on AI models or databases or whatever else that it needs to execute the function. Now, in terms about the RAG and RAG graph, how does the RAG graph differ from the LangGraph?
So
Doing different.
LangGraph, yes, LangGraph is the workflow that the agent is following. So that as if you're putting you have a task at hand and you're basically naming out the instructions, right?
Good.
And GraphRAG,
yes, go
and
ahead.
GraphRAG is how you're retrieving that information.
I see. Okay.
Yes.
Thank you.
Yeah, of course.
Yeah, so I think the GraphRAG is on the data side creating a structure, and LangGraph on the instruction side creating a
Exactly.
structure.
The task. Yeah.
One question is, Alejandro, how fast are these systems? So how big was your data, and how quickly can you answer these questions?
The times I ran it, it took maybe 15 minutes to go through about 2,000, 3,000 records all at once. So yeah, it's pretty efficient. Like I don't think a human could do that in 15 minutes, but so in a sense, it's bringing efficiency into like any workforce, anything that you could think of, pretty much.
Yeah. Thank you.
Yep.
Any other questions?
Any other questions?
Alejandro, if there are no more questions, I will have another question. We are trying to identify our alumni on LinkedIn. Could this LangGraph help us with matching which students we have information on? We don't want to do
Probably,
it
yeah.
manually. Can you help us with
Of course. Of course.
that? Okay, that's
That could
great.
happen 100%. All we need is, their information, technically.
And can that script keep running all the time? So if the alumni changes jobs, we automatically learn about it?
That I am unsure of. I don't know, but probably. I want to say probably, just because technically you could just keep running a script over and over and just and like keep it refreshing. So yeah, that would be a
Okay.
pretty good project, actually.
Yeah, I will send you a list of emails and the LinkedIn page I will create.
Okay.
Yeah, let's do
Perfect.
that.